All right, I suppose we should start. Last time, you probably remember that we generated molecular orbital diagrams, or this one for water, and we did that by combining oxygen atomic orbitals and hydrogen salx. And to get the salx, we basically just guessed. We just took the oxygen atomic orbitals and we tried to figure out what would match, basically. And we came up with these two guys here and here, and those matched. This one matched the s orbital on oxygen, and it also matched the pz orbital on oxygen, so it could overlap with those two guys. And then this one matched, I think that we defined it as py. And so we basically just generated these salts by guessing. And I told you that we could do this every time, except with more complicated molecules, it gets harder and harder. And so there's a system that we can use to generate the salts with more confidence and systematically instead of just kind of hoity-toity. All right, so today we're going to talk about symmetry and group theory. So why do we care about symmetry? Symmetry is useful for telling us about structure. And as you probably know, structure gives us a lot of information about the function of a molecule. So we were just, I was just reminding everyone of what we did last time. Oh yay, hi. Okay, so last time we generated this molecular orbital diagram of water, and we did that using the atomic orbitals of oxygen and these salts, which we could kind of just figured out by looking at what might match the orbitals on oxygen. So the salts looked like these two red dots here and these two red dots here, and we said that this one matched the pz orbital and the s orbital on oxygen, and this one over here matched the py orbital on oxygen. So we just kind of looked at the atomic orbitals on oxygen and guessed what the salts might look like, but we can do it better or with more confidence using group theory and symmetry. So we care about symmetry in general because it tells us about structure, and structure tells us about the function of the molecule. So I'm going to give you some random non-chemistry examples. So my coffee cup, for example. You see this every day when you come to class and drinking out of it. So this coffee cup has a structure, and it's well designed for its function. So it's cylindrical, it has a bottom, an open top, there's a handle on it, and it holds liquids, and I can drink out of it. So its structure is important for its function. Another example is my shoe. My right-hand shoe is shaped like my right-hand foot, and it wouldn't fit my left foot, and it wouldn't fit my hand very well, but it fits my foot pretty well. So the structure of my shoe fits the function. Just like those two examples, a coffee mug and a shoe, the structures of molecules are also important for the function of the molecule. So molecules also have structure-function relationships. Specifically in inorganic chemistry, we're normally talking about the molecular geometry around a metal center. So the molecular geometry around metals lead to electronic properties, magnetic properties, and reactivity, so its function. So the molecular geometry of a metal center is its structure, and it correlates with the electronic and magnetic and reactivity properties. So we're going to apply symmetry arguments to solve real problems in this class. If you know the structure, the molecular geometry of the metal center, you also know something about its bonding, you can interpret spectroscopic data, and you know something about its chirality. So the three real useful things about symmetry are in describing bonding, or in other words, constructing molecular orbital diagrams. So constructing MOs, or in other words, describing bonding. The second is that you can use symmetry to interpret spectroscopic data. vibrational and electronic spectra in particular. So because the structure of the molecule defines its electronic properties, any kind of electronic absorption spectra, like UV vis, can be interpreted using symmetry, as well as vibrational spectroscopy, which also depends on the shape of the molecule. So basically from spectroscopic data, you can also determine structure. And a third thing it's useful for is determining whether something is chiral. So we're going to use group theory, and group theory is just something called symmetry elements that are organized into groups. So symmetry elements organized into groups is called group theory, and those groups are called point groups. So I'm going to write symmetry elements organized into groups, which are called point groups, is group theory. So symmetry and group theory are very closely linked. I'm going to define a few things here. Something called a symmetry operation. A symmetry operation is something that you actually do to the molecule to move it into a new orientation that is indistinguishable from its original orientation. So a symmetry operation is something that you do to move a molecule into a new orientation that is indistinguishable from its original orientation. So what do I mean by that? I'm going to borrow this from you. So if I take this octahedral molecule, and so if you look at this, and then you close your eyes, flip it, and then you look at it again, you wouldn't be able to tell the difference, because all of the atoms, or all the little white balls are the same. So you couldn't tell the difference between this and this. It looked the same. This is a rotation. It's a 180 degree rotation. And the symmetry operation that I'm doing is called a rotation. So I'm moving the molecule so that it's indistinguishable from its original orientation. A symmetry element is the thing that I'm moving around. So in the case that I just showed you, I was rotating. Anytime you have a rotation, you have to have an axis of rotation. So a symmetry element would be that axis. So there's lots of different types of symmetry elements. A symmetry element is a point, a line, or a plane about which a symmetry operation is performed. Okay. So now I want you to play with models to see what these things look like. I've given each of you an octahedral molecule, model of a molecule, and a trigonal bipyramidal molecule. And I'd like to start with the trigonal bipyramidal molecule. So pick up that guy and notice where the axial ligands and the equatorial ligands are. The axial one, well, the equatorial ones are easier to spot. It's the one with the triangle. So I'm going to draw, so I'm going to call this fun with models. And I'm going to draw a trigonal pyramidal, or bipyramidal. And I'm going to label the positions. So the axial positions, I'm going to call A and B, and the equatorial positions, I'm going to just number 1, 2, and 3. So I will just point out one of the symmetry elements, and that is there's an axis of rotation right down A and B. So if you look right down the axis of rotation, or the axis of the axial ligands, there's a rotation that you can do. How far would you rotate it so that it would look the same? You rotate it 180 degrees around that axis? No. What would you do? Yeah. Good. It's 120. Okay. Yeah. She said it exactly right. It's 360 degrees divided by 3 because there are 3 identical ligands in that plane. So anytime you have a rotation axis, it has a special name. It's Cn, where n is 360 divided by the angle of rotation. So in this case, what's 360 divided by 120? Yeah, it's also easy to see that there's 3 identical ligands. So this is called a C3 axis of rotation. And if we rotate it 120 degrees, for example, I would get a molecule that looked exactly the same, except if I actually kept track of the numbers, I might call this 1, 2, and 3 now. So this is the 120 degree rotation. So this is 1C3. That is 1C3 rotation. There's actually a second C3 rotation. If you rotate it one more time, 120 degrees, you get the molecule in a different orientation that's still indistinguishable from the first. So if I rotated it one more time, then 1 would be over here, 2 and 3. And this would be A and B still. So do you see how you can go 2 times and you can get 2 different orientations? What if you ended up at the third, like if you did 3 times? It's exactly the same. And so that one actually doesn't count. So that's the same as something called the identity. So one thing I didn't tell you is that whatever orientation you start with, every molecule has something called the identity, which is basically what you think of as where it starts. So the identity is called E. And that's basically doing nothing to the molecule. So you would end up again at the identity. So I rotated a third time for 120 degrees. I'd be at E. So in total here, we have one C3 axis, which is the element, and we have 2 C3 operations. So that's 2 total C3s. So this one, the first one is just called C3, and the second one is called C3 squared, or it can also be C3 minus 1. So for example, if you started with the identity and you rotated clockwise, that would be C3. If you rotated twice clockwise, you'd be at C3 squared, but if you started from the identity and rotated counterclockwise once, that would be the same as the C3 too. You wouldn't be able to tell the difference. Everyone following that? Okay. All right. So what are the other symmetry elements in this molecule? Tell me what another one is. So we have the identity, and we have 2 C3s total. Yep, there's a planar one. I want you to find one more rotation axis before we go to a plane, though. There's one more rotation axis. Does anyone see it? It's right down one of the ligands. Okay, so if I draw this again down here, there is an axis of rotation here that you can rotate 180 degrees. So what would that be called? If I'm rotating by 180 degrees, what? Yep, it's a C2. So this is going to be my C2 axis. How many C2 axes are there?
Oh, okay.
Yep. So there would be one C2 axis down bond number 1 here, there would be another one going on bond number 2 and another one on bond number 3. So there's 3 different C3 elements. So in this case, we have 3 C3 elements. And how many operations do we have for each one of those? So we have 1 C2. What happens if you do C2 squared? It's the same, right? So there's total of 3 C3 things that we have because there's only 1 operation for each. Okay, so you said that there's a mirror plane. Which one were you talking about? Okay, so it looks like she's doing in the plane of the paper, basically. Oops. Right? Thank you. I do. There's 3 C2 elements. All right, so this is a mirror plane, and mirror planes are designated with a sigma. And there's different subscripts that we use depending on what the mirror plane looks like. So a sigma V is a vertical, and it's vertical with respect to the principal axis or the highest order axis. So the order is basically this little, so with my C3, the order is 3. With the C2, the order is 2. So my highest order axis is C3. And this is, well, the C3 axis is in that mirror plane. And so you call it a sigma V. There's another one that's called a sigma D, which is very similar to sigma V, except this bisects bonds and doesn't go through any bonds. So you can see here, this mirror plane actually goes through bond number 1. It also bisects 2 and 3, but they choose to call it a sigma V in this case. And sometimes you'll notice that there might not be a clear reason as to why they've labeled something V or D, but most of the time it's pretty obvious. If it's not obvious, it's hard sometimes to figure out why they did it. But in general, V goes through bonds and T goes between bonds. Any other mirror planes? Oh, okay. It's the plane that goes through, it's in the plane of the page. Okay, so it's going through this bond, and this bond. And so it's reflecting this atom. Oh, okay. Okay. So I'm just trying to draw that on paper. Not.
Can you say the rules again? Like
if the mirror plane is coplanar with the principal axis, it's a sigma V or a sigma D. Okay? If it's bisecting 2 bonds, if it's bisecting bonds rather than going through bonds. So like this mirror plane in particular is it's coplanar with bond number 1, and it's bisecting 2 and 3. Because it's coplanar with 1, you call it a V. But if this were a different molecule and 1 wasn't there, it would be only bisecting an angle, then it would be a D. So D means dihedral.
So if it was like 4?
Yeah, if it's an octahedron, yes, that would be a sigma D.
So, I mean, it's the same if you were like to rotate it, but just like.
Yeah, so there's 3 different mirror planes that are sigma V. So there's 3 of those guys. Total. But there's a different type of mirror plane. It's not the sigma V, but it's a different one. It's actually perpendicular to that mirror plane. And it goes through bonds 1, 2, and 3. And this one, so I'm going to try to draw it, this one will be perpendicular to the principal axis, and so it's called a sigma H. H is for horizontal with respect to that principal axis. So I'm going to try to draw this going horizontal. So the sigma H is much different from the sigma V in the fact that it's perpendicular to the principal axis. Those are all of the elements that are easy to find. There's one more, and it's called an improper rotation. I'm going to redraw the molecule here. It's a way to put the molecule in an orientation that you couldn't access unless you did two operations simultaneously. So first you do a C3 or a CN, depending on what the molecule is, but in this case you would do a C3 followed by a sigma H, and you would end up getting These are pretty hard to find. This is an improper rotation. And it's called S3 or SN. In this case, it would be S3. So it's named for the principal axis that you're rotating around, but instead of C, it's called S. This is improper rotation. And there's one more type of operation that this guy does not have, and that is an inversion center. So I'm going to write a chart down here of all the symmetry elements and their meanings. Okay, so the easiest symmetry element is one that every single molecule always has, the identity. And this is when you take a molecule and you do nothing to it. So there's no rotation, no reflection, it's just itself, and the symbol for that is E. A mirror plane is another type of symmetry element. The operation is a reflection, and the symbol is sigma. And we just talked about how you can have sigma V, sigma D, or sigma H, depending on its orientation with respect to the principal axis. You can also have a center of symmetry. And this is one that the molecule that we were just looking at does not have. It's called, or the operation is called an inversion. And the symbol is just a little I, a little cursive I. We've also seen already axes of rotation, or an axis of rotation. When you have an axis and you rotate around it, this is called a proper rotation. It's designated by the symbol CN, where you rotate 360 degrees divided by the number. So N is equal to 360 degrees divided by the angle of rotation, or that's another way to write it. And then the last one is an axis of improper rotation. It's called an improper rotation. And the symbol is SN. So this improper rotation, again, is Cn followed by a sigma h. So now what I'd like you to do after you're done writing is take your octahedral model, and I want you to see how many symmetry elements you can find. Write them down on your paper. I'll give you a few minutes to do that, and you can talk about it if you want to. It's actually really hard to find all of the symmetry elements in an octahedron. Let's go down the list. Does it have an identity? Oh, what?
Okay, so I guess we won't answer it. We'll answer it.
Well, go. No, ask your question.
Okay, so right, this is like C4.
Yeah, it is.
Okay, so then and then also C2.
It is.
There are two different. That's two different.
But two different things. Yeah. But C4 squared would be a C2.
Yeah.
So you count the C4 squared as a C2 rather than another C4.
So it's two C2.
Yeah, there's C4, and then there's C4 minus 1, or to the negative 1, and then there's a C2. Yep. Okay, so we have the identity, obviously, so I'm going to just list the elements. We have the identity. What about a mirror plane? Does anybody see mirror planes? Which ones do you see? How many of them do you see? It's hard. In the octahedron, there are 3 different mirror planes that they call sigma h. And that's because they're counting the sigma v's as sigma h. That's a good question. It's because in the octahedron, so here's one orientation, okay? Here's your principal axis. This is your sigma h. This is the same as the principal axis, and it's horizontal mirror plane of sigma h. So the sigma v in this, if you count this is the principal axis, the sigma v here is actually horizontal to this. And because it's so symmetric, the perpendicular rotation axes are all the same. So that's why they're counting sigma v's as sigma h's. There are 3 of those. There's also another type of mirror plane, though. So if we've taken care of what?
I just have H.
H and V.
Yeah.
What are you counting as V? Oh, that's still an H. It would be an H or a V, and they're just lumping them all together and calling them H. What's the other type of mirror plane you can have? A D. Yeah. So do you see any mirror planes that are bisecting angles? So if you look at this molecule, sigma D, okay, perpendicular to that, another sigma D. If you rotate this, so the other way, so this is one, this is one. So kind of going like a karate chop forward and a karate chop at yourself. So those are, so there's actually 6. There's 6 sigma Ds. What about a center of symmetry? It's an inversion center. Okay, so here is the center of the molecule, and if you took point A through the inversion center to the equal distant point on the opposite side, they would be the same. So this is kind of like what we're doing. This is exactly the same, actually, what we're doing with the orbitals when we're talking about whether they were G or U. And we said if we went through the inversion center to the other side, it would be the same or not. So if you can take the molecule, so if you look at your octahedron, if the center of this is the inversion center, this is the same as this, this is the same as this, this is the same as this. So it does in fact have an inversion center. So it has I. Does it have improper rotations? Yeah. They would almost be the same, except when you took the rotation, you'd rotate it, but then it would be different than the rotation because the top and the bottom would switch. So there's actually, I have S4 written in my notes, but I don't have how many there are. There must be 3 because there's 3 principal axes. What about rotation axes? So you said that there were C4s and C2s. I'm just going to tell you how many there are. There are 6 different C4s. There are 3 C2s. And the C2 is just basically C4 squared. And there's 2 more things that we didn't count. And one of them is the C3. There are 8 of them. These are hard to find. Can anyone find the C3? Find a triangle somewhere in there. So if you have to kind of take the octahedron and tip it so instead of looking at it straight on, you have to kind of tip it so that you are looking at a triangle in the front and a triangle in the back. And then if you rotate that angle 120 degrees, it will be the same. And from that same axis, there are 8 S6s. So in this case, you couldn't rotate 120 degrees and then reflect because the atoms wouldn't be in the same place. But you can rotate 60 degrees and then reflect, and you would have an S6. So in this case, notice that the 6, there is no C6 in this molecule. All right. So what if I asked you to find all of these elements on a test? Do you think you could do it? No. Fortunately, there's an easier way. And we don't have to find all of the symmetry elements. If you can just find a couple of them, you can put them in something called, you can put your molecule in something called a point group, and then the point group has a list in something called a character table. You basically can go to the back of your textbook and you can look for your point group, and it will list all of the symmetry operations that that molecule has, and you can relax and not worry about missing anything. So that is what group theory is all about. So group theory involves grouping things with a similar set of symmetry elements. And it groups these things into point groups. Things that are put into a given point group, so for example, the octahedral molecule that you're just working with is grouped into something called the OH point group, or the octahedral point group. There are other things that are in that octahedral point group that don't look like like the traditional octahedral molecule that you're used to seeing. And so anything in that point group would have similar sets of properties. So when you have things in a point group, they'll have similar properties. And I'm going to give you an example. So water is in the same point group as cisplatin. And if you remember what I told you about cisplatin, then it's a cancer therapeutic. Water isn't a cancer therapeutic, but these two guys will have similar spectroscopic properties and similar electronic structure, similar vibrational spectroscopy characteristics. So these guys are in the same point group. A point group is just a set of symmetry operations that describes a molecule's overall symmetry, or a thing's overall symmetry. You could put my shoe into a point group if you wanted to. You can put a coffee cup into a point group. So a point group is a set of symmetry operations that describes the molecule's overall symmetry. So fortunately, if you want to know about a molecule, you don't have to find all of the symmetry elements to assign point groups. You can just follow a very simple flow chart. And the flow chart that's in your Shriver and Atkins textbook is not the easiest to follow, in my opinion. So I'm going to give you the steps that I learned when I was in undergrad, and this is from the Miesler and Tar textbook. So I think Miesler and Tar has a little bit better way of doing it. They're very, very similar, but I like Miesler and Tar's better. So assigning molecules to point groups is what we're going to talk about now. And I think that if you were in Dr. Ocean's class, you learned the way Miesler and Tar teaches it. You guys didn't have that textbook, did you? Miesler and Tar? Oh, okay. I bet you he used Miesler and Tar's way, though. Okay, so the first step, or the first question to ask yourself is, does it belong to a low symmetry group? Things of low symmetry have very few symmetry elements. So I'll give you a few examples. You probably saw this example when you're talking about chirality in organic chemistry. So this is a tetrahedral carbon atom that has 4 different groups on it. This guy has no symmetry other than the identity. There is no reflection plane, there's no rotation axes, no inversions or inversion centers. So this guy has no symmetry elements other than the E. So so if this is your situation, if there's no other symmetry elements, this is characterized, the point group is called C1. If you only have a mirror plane, only one mirror plane, here's a molecule that's an example. So only one mirror plane. And in this case, the mirror plane is in the plane of the molecule, or in the plane of the page as I just drew it. There are no other symmetry elements here, except for the identity. So here, this one would also, of course, have the identity. This one's called CS, is the point group. Only one mirror plane and the identity, it has CS. And then if it only has the identity and a inversion center, this one's called CI. And there are very few molecular examples of the CI point group, but this is one of them. And this molecule would have to be in its staggered conformation to be classified as a CI. If you put it into oh my gosh, what do I want to say? Eclipsed conformation, it would no longer belong to the same group. So sometimes the textbook or I will ask you about a specific conformation of a molecule when I'm asking you to classify these things. All right, so the second thing you want to ask yourself, if it doesn't belong to a low symmetry group, does it belong to a high symmetry group? So, examples of high symmetry groups. Tetrahedral molecules. Now, notice that when we usually talk about tetrahedral carbons, it doesn't necessarily mean that it's in the tetrahedral point group. For example, the first example I gave you up here, that was a tetrahedral carbon, does not fit into the tetrahedral point group just because it's carbon and it's a tetrahedral geometry. You actually have to have symmetry belonging to a tetrahedron to be in this TD point group. Another one is the octahedral point group. This is another high symmetry group. I'm just drawing little L's for ligands. So if you see an octahedron, it belongs to the octahedral point group. There is something called the icosahedral point group, and this one is really hard for me to draw, but I'll do my best. And you won't see very many examples of this in my class. But so the molecular formula here is B12H12 2-. It's probably better to just look in your textbook than to try to go off of my very poor drawing of this guy. So it's highly symmetric, and you can, if you would ever run into something like this, you could tell that there is something special about it. There are two more. Anytime you have a linear molecule, you want to ask yourself if it's a high symmetry group. So if you have something like carbon dioxide, it's a linear molecule. This guy has a C2 axis. I'm going to draw it in red. C2. So you can rotate around there 180 degrees. It would be the same thing. And it also has this axis of rotation. This axis of rotation is C infinity. When you have a C infinity, when you have a linear molecule, you will always have a C infinity. You have C infinity and a perpendicular C2. This is D infinity H. If you have a linear molecule, then it always will have a C infinity. But if you have a linear molecule like HCl, where there isn't a perpendicular C2 axis, this one is C infinity V. And so the tetrahedral, octahedral, or D infinity H and C infinity V are the most common. You don't usually, I didn't write the other one, sorry. This B12H12 is icosahedral, and it's IH. We won't run into that one very often. Okay, so if it's a low symmetry group, you can just classify it and stop. If it's a high symmetry group, you can classify it and stop. But if not, you have to go on to the next question. And number 3 is to do. You have to find the highest order rotation axis. After you find that, if there is not a perpendicular C2 axis, so perpendicular to the highest order axis, so if there's not a perpendicular C2 axis with respect to the principal axis, or the highest order rotation axis, I'm using those two things interchangeably. Does that make sense? The principal axis is the same as the highest order axis. Then the molecule is a single axis group. And so your single axis groups are, first, it's CNH, so H for horizontal, if it has a horizontal mirror plane, or a sigma H. So I mean horizontal with respect to the principal axis. So an example of this is this molecule, where I have a C2 axis. So if it would be coming out of the plane of the paper. So you can rotate here 180 degrees. The rotation axis is coming straight at your face. See that? You can rotate. So that's your principal axis. And there's also a horizontal mirror plane, which is in the plane of the paper. So that would be C2H, because the C2 is the principal axis, and you have a horizontal mirror plane. Next, it's CNV if it does not have a sigma H, but it has a sigma V. So remember that vertical, V is for vertical. It's the sigma V would be in the same plane as the principal axis. An example of this is NH3. So this one has a C3 rotation axis in plane with the lone pair. And it has a sigma V in the plane of the page as drawn. It would actually have 3 different sigma V's. And this would be C3V, point group. Okay, this continued C, it's called just a plain old CN if it doesn't have any mirror planes. An example is this funky molecule. So the thing is, the hydrogens are pointing kind of up out of the plane. And so there is a C3 here, but there's no mirror plane anywhere in the molecule because the hydrogens are out of the plane of the molecule. So this would be just a C3 point group. And the last thing for the single axis groups, if it has an improper rotation, it's S2N. Yes. If it has an S2N axis, collinear with CN. This is rare. So S2N is kind of, we saw an S2N in the octahedron where you had a C3 and then you had an S6. So 2 times the number of the principal axis. These are rare, so they're things that you don't often have to worry about. So those are the cases when you have a principal axis, but you don't have a C2 axis perpendicular to that principal axis. If you do, so if it does have a C2 axis perpendicular to the principal axis, then it is a dihedral axis group. And we represent these groups with D for dihedral. So if you have your principal axis and you also have a C2 perpendicular axis, it's a DNH if there are what? Can you guess? What's the H for? Yeah, it's a DNH if there are horizontal mirror planes. So a mirror plane perpendicular to that principal axis. An example is eclipsed ferrocene. So I have an iron in the middle, and then I have aromatic cyclopentadienyl anions on the top and the bottom. Here we have, right down the center, there is a C5 principal axis. There is also a mirror plane that goes right through the iron and between the 2 cyclopentadienyl anions. So this one is eclipsed ferrocene, and its point group is D5H. So that's the highest symmetry you can have in a dihedral group. It's a DND if there's no sigma H, but you have a sigma D. And remember, sigma Ds are, if you see a sigma V in the dihedral group, it's actually a sigma D. So an example of this is staggered ferrocene. So this is ferrocene staggered. And again, here's your principal axis. It's C5. But now you don't have a mirror plane, a horizontal mirror plane where I had drawn before, because the cyclopentadienyl anions don't reflect on each other. But there is a mirror plane right basically collinear with that C5 axis. So this one is staggered This one is D5D. And then the last one in this group is DN if there are no mirror planes. An example of this is when you have an octahedral complex where the ligands are chelates. So this would be a bichelate or a bidentate chelate, like ethylene diamine. So this one, you actually have a principal axis of rotation. It's similar to where the octahedral, remember the triangle when we were looking at the octahedron? There's a C3 rotation axis there. There's a C2 rotation axis. It's hard to see. Actually, no, it's not. There's C2 rotation axis there, but there are no mirror planes. So this is a D3 group. And then the last group, 5, if you can find no rotation axes, if there are no rotation axes that you can find, you basically go back to the beginning. Go back to the low symmetry groups. C1, if only E. Ci, if E plus an inversion center. And Cs, if only E plus a mirror plane. So now I'm going to write out this, let me give you one example of that molecule. So for example, this guy, where the fluorines and the oxygen are out of plane with the sulfur. So here's your flow chart. So it is a low symmetry group. Yes, then you have C1, CS, or Ci. If no, then you ask yourself if it's a high symmetry group. If it is, then it's going to be either a tetrahedron, an octahedron, icosahedral, C sigma V, or D infinity H. If no, then you find the highest order rotation axis. And then you ask yourself, does it have a perpendicular C2 axis? So perpendicular C2 axis, one that is perpendicular to the highest order axis. If it does not, then you're in a C or S group, a single axis group. Then you ask yourself, does it have a sigma H? If yes, then it's CNH. If no, you ask yourself, does it have a sigma V? Oops, that's ugly. If it does, then it's a CNV. And if it doesn't, then you ask yourself, does it have a C2N, or sorry, S2N, so an improper rotation? If it does, then you've got S2N point group. And if it doesn't, then you're just at CN. So all of the things in pink boxes are point groups that you can characterize things into. So go back up to this part that says, does it have perpendicular C2 axis? If your answer was yes, it does, then you're in a D group or a dihedral group. And the next thing you need to ask, again, it follows the same process as the C groups. Does it have a sigma H? If it does, then you're in DNH. If not, you look for sigma D. So remember, sigma D is analogous to the sigma V over here in the C group or C and S groups. If it does have a sigma D, then you're in DND. If not, then you can stop, and you should be in DN. And if you couldn't find the principal axis, or you couldn't find, the highest order rotation axis, that means you need to go back to the beginning. Questions? Is this pretty similar to what you guys learned in Dr. Urson's class? It's easy for you guys, right? Okay. How are you doing, Haley? Okay. So there's some problems in your homework where I'm asking you to assign things to point groups. I want you to start practicing. Now, did you ever go back to try to find Orbitron?
Yeah.
Did you find it? Oh, good, okay. I was going to put a link to Orbitron, and then there's another website that can help you visualize where these things are. They actually have three-dimensional molecules on the computer, and they show you where all of the symmetry elements are. So I'm going to post a link to that as well on your Blackboard resources or your course materials folder.